Hi, I'm Dasher Keeler, and this is my Sling Cam. I built the camera to introduce myself to the world of embedded hardware and to gain experience with Arduino. The concept was to create something to approximate a rocket payload and to bring it back safely. After some arduous cross-referencing for compatibility, I purchased all of the necessary components from the Adafruit shop for $140. Sure hope this works. I got to work on testing the components and getting up to speed with Arduino coding. I overestimated the difficulty of this part of the project and quickly moved on to the next phase of development, soldering. Really more a combination of soldering and trying to figure out how to organize each component so that it would fit inside of a cardboard tube. The resulting abomination fits inside spectacularly. However, if some of the connections need to be repaired, I would undoubtedly need to undo a great deal of work to get to the trouble location. A definite trade-off, but a great motivation to make sure the parachute system works reliably. Once my tangle of wires was operating correctly, I started to work on the mechanical parts of the system. My initial design for a release system worked great, but left extremely limited space. This was an issue I hoped to solve on the parachute design side by creating a very space-efficient chute. Each parachute was created from the thinnest material I had access to and could work with, shopping bags. With sufficient heat from a clothes iron, you can weld them together. As I delved deeper into testing my first parachute design, I realized that it was just barely creating enough drag for a safe landing, and even wrapped up tightly, it still took up to 3 times the available volume of its storage space. I decided to scrap my first release mechanism and create a new design around a vastly larger container. With this larger container, I ran a few indoor tests to see how the parachutes would deploy from their housing. They did not. Upon seeing this, I designed an ejection system that would force the parachute out of its housing once it was released, exposing it to the airflow and hopefully opening before a hard landing. This new system worked fantastically at pushing out the parachutes. However, the force of the ejection system was too powerful for the current attachment system, pulling itself apart almost instantly when it was given the chance. I then had to design a new release mechanism that could withstand the ejector's force. Finally, with a solid and exceptionally consistent release mechanism, I started working on testing the parachutes to make sure that they would be at least as consistent. To this end, I created a simple device that would let me release the parachutes and expose them to the air at the peak of their trajectory, rather than getting a head start unfurling on the way up as they would if simply thrown by hand. Alongside this, I played around with a sort of hand-traced CAD model of an ideal parachute. With the geometry of this parachute calculated out, I fabricated a few versions of it, one of which utilized an even thinner material, grocery store produce bags. This version actually could have fit within the confines of the original release mechanism, but as you have certainly experienced, produce bags are quite staticky and don't particularly like to catch air. Not the best trait for a parachute. In my testing of the parachutes with the various possible configurations and folding techniques, I found a few things. The first was that having multiple parachutes didn't help the overall reliability, as the necessary airspeed and drag to open any given chute would be cannibalized by the first one to open. Effectively, only one parachute would consistently open. The second was that the most effective folding technique for the small parachute didn't transfer to being the best when used with the larger parachute. This was because, with the larger surface area of the new parachute, the earlier issue of not catching enough air to open was mostly negated. So with the benefit of the complex folding technique mostly removed, the issue of the parachute cords tangling upon themselves became a considerable one. In the end, a simple rolling up of the parachute served to be the most reliable. I now have a massive amount of respect for the parachute engineers and spacecraft. It's not as simple as it looks. The final configuration ended up being a single large parachute wrapped up around itself and surrounded by 3 cardboard supports so that it wouldn't be crushed by the force of the ejector. The coding was a step back into the familiar. After refactoring the initial test code, I worked on designing the release algorithm. It ended up being pretty simple, but before I could write it, I needed to know what data I would have available to make decisions from. I logged the data in a fixed duration loop, so that variations in running speed would not affect the accuracy of the logged data. Then, by using a timed release countdown for my maiden tosses, I was able to get a recording of the data that the barometer would see in flight. The noise of the barometer data makes an exact pinpoint of the trajectory's peak fairly impossible, but luckily, the detection of a throw is more important, as giving the parachute time to unfurl on the way up only hastens its opening. The algorithm only needs to be able to distinguish an actual throw versus a spike in the noise. Pressure readings change day to day with the temperature, so I needed a system that was agnostic to any relative variation. To detect this, I took 3 running averages: the total average, a low average, and a high average. Any incoming value lower than the total average would be averaged into the low average, with the total average being averaged into the high average that cycle, and vice versa. The parachute would release when the pressure dropped below a large enough multiple of the difference between the high and low average, effectively letting me use the noise as my release constant. A great benefit of this averaging is that when the camera is thrown by Sling, the windup causes the average gap to increase, automatically accounting for the extra height of the subsequent throw. Finally, after soldering on the camera, I was able to get my first blurry photos back to Earth. By giving a bit of time delay between the parachute ejection and the photo, I was able to cut down on the shaking caused by the ejection. And, if luck would have it, you can get some pretty decent photos from the sky. I think my next foray will be to incorporate an accelerometer or gyroscope to help ensure that the photos are pointing down. I hope this was as interesting to watch as it was to make. Thanks for watching.